Okay, I want to give the precise definition of an infinite limit. And it goes like this. The limit as x goes to a, f of x, equals infinity if given any m greater than 0. And this right here, this m is playing the role of the epsilon in other types of limit proofs. Just we have to somehow make it so that you understand the graph rises and continues to rise above any possible real number. So if given any m greater than 0, there is delta greater than 0, where 0 less than the absolute value of x minus a, make that a little better, is less than delta, implies that f of x is greater than m. So there's our exact definition. Let me prove one of these things. I don't want to spend a lot of time on these, but I do want you to be aware of them and how they play roles in asymptotes and things like that. So as an example, let's prove that the limit as x goes to 2 of 1 over x minus 2, that quantity squared, equals infinity. So as before, let m greater than 0 be given. So let m greater than 0 be given. The effort here is to try to make the definitions uniform. So we're trying to use the same letters. I'm not using epsilon for the y values because I don't want you to think of these y values clustering around a small value. They're actually shooting up beyond any imaginable height. So anyways, what we'd be looking at then, this is my f of x, which is the 1 minus x squared. I need to somehow make it so that 1 over x minus 2 squared ends up being less than, or I'm sorry, greater than m. I need to make that happen somehow. This is my goal. So what I'll do, in fact, I'll put a thing around it so that I don't want it to be part of my proof. It's just something I need to find. Remember, when we're talking about delta, in this case, we'll be talking about 0 less than the absolute value of x minus 2 is less than delta. Now I notice that I have a 1 over x minus 2 squared. So the first thing I'm going to try to get here is an x minus 2 squared. Well, if I were to multiply by the inequality absolute value of x minus 2 times the absolute value of x minus 2, that would have to be less than delta squared. Now, I don't care about the 0 anymore. It's really, in computing the delta, I just don't need that 0 to be around to help me with anything. Luckily, x minus 2, the absolute value of x minus 2 times the absolute value of x minus 2 does happen to be regular x minus 2, but squared. So, in these things, when you start dividing by x minus 2 squared and delta squared, you're going to get this inequality. I'll get 1 over delta squared is less than 1 over x minus 2 squared. And I suppose this is where x not equaling 2 is very important, because I wouldn't have been able to divide by x minus 2 squared if x was allowed to have equaled 2. So that's really good. And the goal, though, was to get it to be greater than m. Remember? So we wanted it to be greater than m. I wanted an m there, not 1 over delta squared. So my scratch work could look like this. 1 over delta squared equals m. Flip delta squared equals 1 over m. And then I can let delta equal the square, or 1 over the square root of m. I don't want to take the negative because I want delta to be a positive number. So that'll be the delta that I'll need to find. When you get that, the epsilon will fall in place. Let me just run through it to show you how it actually works. We would look at the absolute value of 1 over x minus 2 squared in absolute value. is still the same as 1 over x minus 2 squared. In fact, let me back up a little bit here. I didn't even need that part. There was no mention of absolute value in that thing anyways. So 1 over x minus 2 squared is less than what? Well, now that I let delta equal 1 over the square root of m. Okay. So when 0 is less than the absolute value of x minus 2 is less than delta, then as we had before, 1 over delta squared is less than 1 over x minus 2 squared. So this will be 1 over delta squared, which equals m. So there we go. That goes to infinity. And in fact, you should make note, a little note here, the line x equal 2 is a vertical asymptote. For f of x equals 1 over x minus 2 squared. Now, as before, we have the same thing as far as limits are concerned. We have left and right, or I could do negative infinity. All these will have similar definitions. Now let me give the definition of a vertical asymptote. I'll call it D, E, F. That D didn't come out so well, so we'll try again. D, E, F. The line x equals a, and note that that's a vertical line, is a vertical asymptote for f of x if at least one of the following four conditions hold. They are: if the limit as x goes to a from the left of f of x equals either positive or negative infinity, or lim as x goes to a from the right f of x equals plus or minus infinity. Of course, you can have a number of combination of these things, but nonetheless, if any one of those four is true, you're going to have a vertical asymptote. The simplest example I can think of that shows this is the following. Let's let f of x equal tangent of x. Then you probably have seen the graph of this a million times. I'll just draw a really rough sketch here. Let's put this pi over 2, and I'll put dashed lines to indicate that's a vertical asymptote for tangent. It comes in here through the origin, but then skyrockets up. But on the other side, it starts down and starts to go up again, like so. So we know that it's a limit as x goes to pi over 2 from the left is positive infinity. We also know that the limit as x goes to pi over 2 from the right, tangent of x equals negative infinity. So between these two things, the actual limit doesn't exist. So these two imply that the limit as x goes to pi over 2 of tangent of x does not exist. nonetheless, the line x equals pi over 2 is still a vertical asymptote. Can you get it? Can you make it? Well, no period that sentence gets. All right, I think one more example will be fine for me. Let's take a look at the function x squared minus x minus 6 divided by 3x squared minus 4x minus 15. And I would like to look at two cases. Let me look first at find the limit as x goes to 3, x squared minus x minus 6 all over 3x squared minus 4x minus 15. Well, the first thing that this is wild now, but the first thing we try to do is actually plug in the 3's and see what happens. So it'd be my hope that I can put a 3 wherever the x is. It'll give me the answer. Remember, you're allowed to plug it in so long as the number is in the domain of the rational function. Here down here I'll have 3 times 3 squared minus 4 times 3 minus 15. That equals 9 minus, well, 9. This isn't looking good. Then I would have 27 minus 12 minus 15. Well, guess what? We're going to come up with 0 over 0. So this is not going to give me anything. So I'm going to have to factor. But knowing that I plugged 3 in for x and it produced a 0, I know that it's a factor. In fact, we have a clue then how to factor these things. If I take x squared minus x minus 6, since the 3 is a 0, I know that one factor has to be x minus 3. That price a little heavier. So then all I need to do is figure out the other piece. Well, at the end I have a negative 6. And I already got negative 3 here. So I know that this last piece has to be a positive 2. It starts out as x squared, so there's no choice here but to have x. You can FOIL it out if you want, but trust me, it's going to work. Now the other piece works the same way. I have 3x squared minus 4x minus 15 is going to equal x minus 3 times something. First thing I'll look at is the last piece. The last term, negative 15. Well, I've already got negative 3. Negative 3 times what gives me negative 15, and that would be a positive 5. And then since we have to start with a 3x squared, I know I have to have 3x plus 5 as the other factor. So this limit really becomes the limit as x goes to 3 of x minus 3 times x plus 2 all over x minus 3 times 3x plus 5. And of course, since we have x minus 3 in the numerator and the denominator and they completely cancel out, we know there's going to be a hole when x is equal to 3. Now at this stage, since 3 is no longer a problem number, I can just plug it in for x. So I'll have a 3 plus 2 divided by 3 times 3 plus 5. That equals 5 divided by 14. And you can check it out with the calculator. In fact, I encourage you to do so. Another thing I want you to look in the same problem. Tell me what this limit is. Check out this example of what was left over after the x minus 3's were canceled. The x plus 2 over the 3x plus 5. I would like to look at the limit as x goes to negative 5/3 of x plus 2 divided by 3x plus 5. Now, there's a variety of ways to approach this problem. I want to not really use my calculator. I want to stay away from it. You can check the answer later on. But what happens here is I'm going to get a non-zero number in the numerator. So if I were to try to plug it in directly, I get negative 5/3 plus 2 divided by 3 times negative 5/3 plus 5. That would give me 1/3 over 0. Now, some people might think that this means that it's going to be positive infinity for the answer. That is not necessarily so. We've got to see the behavior, whether it's positive or negative, close to the number in question, the negative 5/3. There's no question that negative 5/3 is going to be a vertical asymptote. So something like this is going to happen. I'm just going to draw a very, very rough sketch. Here we have negative 5/3. One way or another, this is going to be an asymptote, vertical asymptote. I think what I would probably do is pick a number that's close to negative 5/3 and plug it in and see where, if it's positive or negative, and that would kind of tell me what's going to happen. So let's take a look at the limit as x goes to negative 5/3 from the left. Now, if you put this in your calculator and graph it, there's nothing to do. You just look at it; it'll tell you which one, positive or negative infinity, it's going to. So in this scenario, I want numbers that are slightly less than negative 5/3. Negative 5/3 is roughly equal to negative 1.67. So I'm going to test x equals negative 1.7. That's close to it, and it's less than it. So let's plug it in and see what happens. I'm plugging it in for x. So I'll have negative 1.7 plus 2 all over 3 times negative 1.7 plus 5. So in the numerator, I'll get 0.3, and in the denominator, I'll get negative 5.1 plus 5. So it'll be negative 0.1. Or if you want to simplify, negative 3. Well, it's a negative number. So what that tells me is that the function comes and does something like this. And by the way, since x plus 2 is in the denominator, it has to actually hit the x-axis when x equals negative 2. Now let's take a look from the other side. Let's take a look at the limit as x goes to negative 5/3 from the right. So this time I'll pick a number slightly bigger than negative 1.67. So I'll test x equals 1.6. Let's throw it in and see what happens. So I have negative 1.6 plus 2 all over 3 times negative 1.6 plus 5. So in the numerator, I'll get 0.4. In the denominator, I'll get negative 4.8 plus 5, 0.2, which is 2. So this tells me that I had to be positive to the right of there. So the graph is doing something like this. In fact, if I think of x equals 0, I can even tell that the y-intercept is going to be positive. So, on the one hand, I was going to negative infinity. From the right, I was going to positive infinity. So this means that the limit, as x goes to negative 5/3 of x plus 2 over 3x plus 5, does not exist.